Awesome. Well, welcome, guys. My name is Priyam Jain, and I am from Gatik. I don't know how many of you guys have heard of Gatik, but we're in the AV space, and I'm going to take this minute and a half and tell you more about it. But when you have more questions, we have a booth set up, and I have a wonderful team of engineers who can talk a little bit more about Gatik. So for folks who don't know, Gatik was founded back in 2017, and we are the leader in autonomous middle-mile logistics. So we were founded back by three founders in the AV space. They're veterans. Our key investors are Koch Technologies, Innovation Endeavors, Goodyear, and Ryder. And guess what? We're also the only autonomous trucking company that's done commercial successful deliveries on public roads by taking the driver out. And we've done it in different markets and with different customers. So the first one was Walmart in 2021. And the second one was Loblaw, which is Canada's largest retail chain store, in 2022. We also have multi-year partnerships with many companies across different verticals who are really ready to adapt Gatik's technologies. So what is the middle mile? I'm sure that's the first question that came to mind. This picture really paints a better picture of where Gatik falls in and what the niche space that we're functioning, which is box trucks, class 3 to class 7. And what we do is we move goods from micro-fulfillment centers to either retail stores, pickup hubs, or from larger distribution centers to micro-fulfillment centers, and they're on. And how we're solving this problem is actually by doing a technology that's built for repeatable B2B routes. And why we're disrupting the market is because this is a $250 billion market. We're barely scratching the surface with some of the main customers that we have, apart from Walmart and Loblaw that I mentioned, is Kroger, Tyson, Pitney Bowes, and Georgia Pacific. So focusing on retail chain stores, but also diversifying to logistic companies and paper goods companies. And that's my timer. Thank you.
Hey everyone, it's great to be here. My name is Gabriel Patton, and I'm representing Autodesk today. So Autodesk is a 3D design company here in the Bay Area. And today I'm representing Autodesk Research. So this is a really awesome organization. We have a ton of different research themes across our industries. So a lot of you might know us for architecture, engineering, and construction, manufacturing, media, and entertainment. But if it's news to you today, we also actually have a lot of robotics research that has gone on for the past 10 years. So our current focus is around adaptive product assembly. And this is a shot of one of our labs up in San Francisco, working on some assembly tasks. So we're looking at problems, everything from the design space through simulation, perception challenges, all the way to physical assembly on our work cells. And we have a really awesome robotics lab up on Pier 9 at our technology center. There's a shot from a couple years ago inside there. You can see the R2K2 unit in the bottom left-hand corner. And we also have a really awesome internship program. And one of our interns is here today. And we are looking for new interns for robotics, as well as other research areas, and some of those internships have just gone online, so keep a lookout. And today we have 3 representatives from Autodesk Research to connect with. So Shri and Nick are up in the back. My name is Gabby, and come say hi, and we would love to connect about Autodesk Research. Thanks.
Hello, everyone. My name is Liang Jun Zhang from Baidu Research, Robotics and Autonomous Driving Lab. Our lab is located at Sunnyvale, and we are looking for academic collaborations and research interns. We work on the construction machinery automations, and such as excavator, which can be think about a mobile manipulator, but working in the field. Our research motivation is that the operating excavator is very challenging because the worker need to work in very harsh environment. Also, there's a shortage of the skilled operators. Towards this goal, we have developed an autonomous excavator system, AES, for construction earth moving by collaborating with the top construction companies. This video highlights the performance of our AES system, which can perform the multiple construction moving tasks, such as the truck loading, autonomous truck loading. As you can see, there's no operator inside the cabin for this excavator. The other tasks include the navigation in the complex terrains and the trenching of the terrain. So our system incorporates the perception, planning, and for the system, yeah. In terms of, there's a lot of research challenge behind the construction robotics because robots need to work on the unstructured environment, and we are looking for the collaboration. Thank you.
Using intelligent robotic systems to automate everything from the inside of the warehouse to the consumer's front door. Today we have 3 next-generation robotic fulfillment centers powered by fleets of intelligent mobile manipulator robots that reliably pick, pack, and handle thousands of customer orders every day. We use AI and deep learning primarily in 2 ways: for multi-agent control using deep RL and manipulation using vision action foundation models. We use a deep reinforcement learning policy trained in simulation across millions of scenarios to control and coordinate our multi-agent fleet of mobile manipulators. Our RL policy learns how to most effectively coordinate dozens or hundreds of robots to fulfill thousands of complex orders by most efficiently navigating through the warehouse and collaborating with other robots to store and retrieve inventory and pick, pack, and sort orders. On the vision side, in this video, we show our robot's ability to handle a diverse set of products, everything from footwear to apparel, electronics, cosmetics, brushes, loofahs, etc. What we're showing in this video is our robot's ability to determine regions on each of the objects where the robot can place its gripper to reliably pick the object up. We're also segmenting and separating out the different objects in the scene to determine different material properties about each of those objects, like is this object big, small, rigid, compliant, porous, like a sponge. We're using all of that information to determine how the robot should handle the item and what type of gripper it should use to handle that item. So you can also see we're densely packing and playing this game of 3D Tetris in real time. So there are 3 things that make our picking system reliable across millions of different objects. The first is the Nimble brain and the AI system that we've developed in-house. The second is the Swiss Army knife gripper, our robot's ability to swap out different types of tools and grippers to reliably handle many different objects. And the final piece is the teleoperator in the loop, which is able to help the robot if it ever gets stuck, and it's also used as a means of collecting more training data for behavioral cloning. Quickly, I'll highlight Nimble's iconic AI board of directors. So Fei-Fei Li, Mark Rabert, the founder of Boston Dynamics, and Sebastian Thrun, founder of Google X and Waymo. Feel free to reach me at simon@nimble.ai. Thanks.
Good morning. We propose automatic waypoint extraction, or ALL, to scale imitation learning to long horizon tasks. ALL is a simple plug-and-play module that automatically breaks demonstration trajectories into waypoints without human supervision. Then, train your policy to predict the next waypoint instead of the next immediate action. ALL decreases policy horizon by up to 10x, and thus reduces compounding errors. ALL can be combined with state-of-the-art imitation learning methods, such as ACT and diffusion policy. It consistently improves the performance and data efficiency on previous benchmarked and real robot tasks. Come chat with us if you're interested in long-horizon decision-making. Thank you.
Hello, everyone. My name is Tony Chen. I'm from BDML here at Stanford. Today, I'm presenting our collaboration with the Laboratory of Organismal Biology on Tabot, a tapomimetic robot that's used for parental care study in American poison frogs, which is one of the only species of frog that evolved to pair bond for life, and together the mom and the dad take care of their offspring. And when the tadpoles are hungry, they beg by this wiggling behavior, signaling to the dad, and then the dad calls over the mom to feed. During phase 1 of the animal study, we were able to convince the dad into making the call every single time, but not able to trick the mom. So we made some improvements, and right now it's in the second round of animal study. Thank you for your time. I'd love to talk to you more about it at the poster session.
Good morning, everyone. Today I'm going to talk about the work that we've been carrying out in the Hyperlab at UC Berkeley about cooperative aerial transportation systems. The key idea is that we would like to use commercial drones, which are widely available, cheap and simple systems, as truss modules to attach to a generic object to transport it and fly it around. The insight is that the attachment locations around the objects are very important synthesis parameters that we can leverage. And so what we do is we formulate an optimization problem which we jointly optimize for layout and controls. We show through experiments that this approach outperform a naive approach in which just the control is optimal. And you can see in the video that jointly optimized system has better disturbance rejection performances. Thank you. Come check out the poster.
Hi everyone, I'm Sophie Leonza, and my project involves a soft robotic arm that can mimic the multimodal deformations of elephant trunks. So elephant trunks, they can achieve a wide range of different deformations, and this is due to the contraction of their differently oriented muscle fibers, such as longitudinal or helically arranged muscles. So we're using an artificial muscle that can contract upon heating called liquid crystal elastomer, and we can achieve multimodal deformations by heating these materials through a muscle arrangement that is quite simplified and rationally designed. Thank you.
Hey everyone. So how can we enable a robot equipped with dexterous hand to perform challenging long horizon manipulation tasks? For example, building a structure from a pile of mega blocks. So in this work, we present sequential dexterity, a general system based on deep reinforcement learning that chains multiple dexterous policy to achieve long horizon task goal. The core of our system is a bidirectional optimization framework, which progressively fine-tunes the sub-policy to enhance the chaining success rate. So the key here is to guarantee that the end-state distribution of the previous skill is feasible for the next skill to start with. For more details, feel free to check out our poster and our website. Thanks.
Hello, I'm Claire, and our project AO Grasp, Articulated Object Grasp Generation, focuses on the first crucial but challenging step of interacting with any articulated object, determining how a robot should grasp it to enable downstream interaction. AO Grasp predicts stable and actionable grasps on objects like cabinets and appliances, given only partial point clouds. We train it on a new synthetic data set of grasps on articulated objects. Despite being trained only on this synthetic data set, AO Grasp proposes actionable grasps on real-world objects with varied geometries and articulation axes in both open and closed states. Please stop by our poster to learn more. Thank you.
Hello, everyone. I'm Wang Gyongdo from Stanford University, advised by Wang Kennedy. This project is about the interfinger small object manipulation with using the dense tech optical tactile sensor. And the object of this project is grasping or reorienting and classify the small objects out of the cluttered environment using our soft optical tactile sensor input. And we successfully achieved 88% of successful grasping rate as well as successful classification result out of the grasping small object out of the cluttered environment. So if you want to check more details about our project, please come by to poster, and thank you.
So given some high-level objectives like clean the room, we equip robots with common sense reasoning skills to be able to follow that instruction. So for example, the video should be playing, but this is how our robot decides. This would have been how a robot decided to clean the room, but trust me, it chooses to clean everything except it leaves that yellow model sports car alone and it leaves the toy train set alone because it looks like it's been built using a lot of effort. And I do want to stress that the robot performs this reasoning all without querying a human. It instead relies on an LLM and a VLM to actively perceive the environment whenever it's uncertain about something. And once it gathers that new piece of information, it then reasons about what to do next. So please come find me at my poster. Thanks.
Hi, I'm Steven. One impressive capability that has been observed in animals like humans, chimpanzees, and crows is tool use. These animals are actually not just able to use tools, they can also select or create the right ones to help them solve the tasks that they're trying to do. So can robots also do that? It turns out to be harder than it looks, because the design of a tool and how you use it are highly interdependent. So we develop a deep RL framework for robots to jointly learn to design and use tools for manipulation, creating specialized tools based on the task initialization or goal. We develop a set of evaluation environments, simple tool design parameterization, and evaluate our policies on real robots by creating the tools in the real world using 3D printing. Please stop by our poster. Thanks.
All right. Hello, everyone. I'm Dhruv, and I'm going to talk about our work for a foundation model for navigation. First, we've heard the F word a lot today, so I'll define it. What we mean by a foundation model is a model that can be once trained, deployed zero-shot, and it can be adapted downstream for a lot of different tasks, like different objectives. And to this, we try to train this cross-robot model, which can be fine-tuned for using new data for new tasks, like new robots. It can be used by prompt tuning for new goal specifications, and by fine-tuning with different objectives, like reinforcement learning. And the code is public. You can download it, as some people already have, and the model is being deployed around the world in different universities. Come by my poster, and we have a robot, and hopefully that'll work, but we'll find out. So come find me. Thanks.
Hi, I'm Yu Chen. I believe future robots will need to learn from non-expert human teachers. Therefore, it is important to harness the right kind of information from such interactions. And for example, non-expert human teachers can provide noisy demonstrations that harm downstream imitation learning. In this work, we show that if we collect additional annotations of action modes, we can leverage action relabeling to train policies with hybrid action representations so that simply doing imitation learning without any reward signals can also learn from suboptimal data. We show that our method can beat baselines by 60% at this challenging long horizon precise manipulation coffee making task. This work will appear at Coral next month. Thanks.
Hi, my name is Ron, and I'm a PhD student in the Autonomous Systems Lab, advised by Professor Marco Pavone at Stanford. Our goal is to build reliable autonomous systems that safely leverage learned components. And to this end, in this work, we ask, how can we avoid closed-loop failures when faced with out-of-distribution observations at deployment? Observations that are dissimilar from training data, on which learned models can behave very erratically, and that will suddenly come up during a deployment. We thought, well, it might be very difficult to robustify a perception system to anything it can possibly encounter at deployment. At the very least, we may try to detect such examples at runtime and use such an OOD detector to trigger a safety-preserving fallback strategy. If you are interested in building robust autonomous systems, please come see me at my poster.
Hi, everyone. My name is Joe. I'm advised by Max Schwager. Today I'll be talking at the poster session about guaranteeing robot system performance using stochastic simulation rollouts. And this addresses a problem where a lot of our dynamics models these days are wrapped up in these very complicated simulators where we don't have the actual equations exposed to us. And it makes traditional analysis of performance very challenging. So we resort to a distribution-free statistics approach where we can certify different measures of risk and different chance constraints. Importantly, in this work, we address the problem of how to use all these statistics to choose the best policy among a set of policies that you've tested. This kind of has some tricky nuance to it that has been missed in the past. So I'll be at the poster session. Thank you.
Hi, everyone. My name is Daniel. I'm in the Nav Lab here at Stanford. In an urban environment, the city infrastructure such as buildings as well as vegetation will block the GPS signals that we ubiquitously use to navigate. That includes people and autonomous systems. Current methods try to predict when a signal will be blocked, but are unable to accurately, precisely, or fully capture the environment. Instead, we propose neural city maps built upon neural radiance fields that allow us to more fully capture the environment, and we develop a method to use this representation with a GPS signal case. With that, I'll be at my poster, and please come check it out. Thank you.
Hi everyone, my name is Cosima. I'm a postdoc here at Stanford with the Charm Lab. In this project, we sought to combine elements of soft robotics with variable stiffness knitting to achieve perceivable haptic feedback. We built 3D printed soft actuators and embedded them into a sleeve, enabled to control the stiffness locally through heat treatment. We tested this haptic feedback in a user study and showed that compared to vibration, the usual mode of actuation for haptics, we achieved better localization results. We also showed that because it's entirely soft, and because the features are designed to fit to the 95th percentile of the population, users thought our design was very comfortable and very, very pleasing to look at. We predict that this concept has many applications, including VR, AR, teleoperation, and navigation. For more details, come see me at my poster.
Hey everyone, I'm Arik from the Stanford Intelligent Systems Lab, and me and some of my lab mates have been recently investigating safe planning under uncertainty, modeled through constrained, partially observable Markov decision processes. So CPOMDPs model planning with hard constraints under both state and transition uncertainty, but they're really difficult to solve, especially in large problem domains, which often arise in robotics. So recently, we've investigated extending online planning methods to small continuous domains, then by using hierarchies to scale them to much larger domains, like this constrained, partially observable robot localization problem here on the right, and I'm happy to discuss these and ongoing works at my poster. Thanks.
Hi everyone, my name is Edward Zhu from UC Berkeley, and the problem that I'm considering here is that of head-to-head autonomous racing, which is a scenario in which agents engage in competitive and highly dynamic behavior without any information sharing, and also where safety in the form of collision avoidance is critical. So in these scenarios, our objective is to both predict the behavior of a target vehicle and to then solve for control actions for an ego vehicle. And our solution approach uses a Gaussian process prediction model in order to capture the one-step closed-loop behavior of a target vehicle conditioned on the control actions of an ego vehicle. We then use the uncertainties from this prediction model to tighten collision avoidance constraints for the ego vehicle MPC policy, and we demonstrate our results on in head-to-head races on 1/10 scale hardware at speeds of up to 2.8 meters per second. So thank you.
Hi everyone, my name is Amber and I'm from the Embodied Dexterity group at UC Berkeley. Burrowing on granular media is a very challenging task for robots to be able to do due to upward resistive forces from the granular media. However, it's a very easy task for the Pacific mole crab, which can burrow very fast as it's avoiding predators. My predecessor, Laura Triers, designed the Amaretta burrowing robot inspired by the Pacific mole crab, which was one of the first legged robots capable of vertical self-burrowing. However, we noticed there were two failure modes as it would burrow that can be described by its changing body pitch. So we designed a second version of the robot, Ember 2.0, capable of body pitch control. To learn how that happens and to meet the robots, come check me out at my poster. Thanks.
Hello, I'm Xinghao from UC Berkeley. Can robot directly learn from human demonstrations by just observing them through RGB videos? Our recent works propose to learn from scalable human demonstration dataset in a model-based manner. This work estimates the object pose and shapes and subsequently generate model-based context-aware manipulation plans, harnessing the power of differentiable simulation and rendering. Then a newer policy imitates the model-based generated plans and successfully deployed to real-world dexterous manipulation and novel objects. For in-depth understanding, please come check out our posters. Thank you.
We present Reflect, a general framework for both human and robot to better understand failures. The framework takes in multi-sensory observations from the robot task execution and outputs a natural language failure explanation, which either helps a human to debug the failure or the robot to generate a correction plan. Our approach uses pre-trained VLMs and ALMs to convert raw sensory data into a textual summary of the robot past experiences, which is then used to query an LLM for failure explanations. By leveraging the common sense reasoning ability of LLM, our framework makes no explicit assumptions on tasks or failure types. To learn more, please visit Ms. Yi at the poster session. Thank you.
Hi everyone, I'm Biko. It's my great pleasure to present our recent work, Learning Humanoid Locomotion with Transformers. It is a joint work with Ilya and Tete. In this work, we demonstrate a humanoid robot can work under various disturbances and over different terrains. We achieved this by adopting a transformer-based policy trained in a teacher-student framework, joint optimized with imitation and reinforcement learning. We performed parallel training and then sim-to-real transferred to hardware zero-shot. For more details, please check our website and come to our poster session. Thank you.
Hi, my name is John, and I'm very excited to share SpawnNet. Given demonstrations of picking up a small set of bags, how can we generalize to pick up many unseen bags? One direction is to leverage the semantic information captured in pre-trained features. However, there exists a visual gap between internet pre-training data and in-domain robotics data. To address this bottleneck, we propose SpawnNet. By fusing frozen pre-trained features and domain-specific features learned from scratch, SpawnNet learns robust and task-specific features, such as attending to the handle when grasping, even for unseen bags. SpawnNet shows significant improvements over pre-trained and from-scratch baselines, especially with novel objects in both simulation and real-world setups. For more information, please check out our poster. Thank you.
Hi, my name is Antonio, and sorry for this video. Here we go. Awesome. So again, my name is Antonio. Ever wonder why robots in the wild are always alone? In this work, we propose an approach to enable a robot to information gather, strategize, and predict while interacting with other agents in unstructured environments, all from a single onboard RGB camera. More specifically, we train our robot to play a game of tag, either with other robots or with other humans, doing test time adaptation to the agent it is interacting with. Our policy is trained exclusively in simulation, and we notice that transfer is dependent on a delicate balance between optimality and diversity of behaviors. Come to our posters to learn more. Thank you.
Hello, I'm Chungmin from Berkeley's Auto Lab, presenting LERF, Language Embedded Radiance Fields, and our choral paper using LERF for task-oriented grasping. LERF embeds clip features volumetrically into 3D, resulting in a 3D scene representation which can be queried with natural language. It has a multi-scale understanding of the world, which can be used for querying large objects as well as their parts. We leverage this property for task-oriented grasping. Given object and part queries specified by natural language, the robot queries LERF to generate semantically meaningful grasps. Please come to our posters or scan the QR code to find more. Thank you.
Hello, my name is Ahad Rof, and my research is on smart skins for soft robots. Traditionally, soft actuators and sensors are made on elastomeric materials like the silicone, but soft manufacturing processes often have issues scaling to make large actuator and sensor arrays. My research is on aesthetic and Kurigami form factors for flexible printed circuit boards, embedding electrostatic layer jamming, and capacitive sensing for scalable, low cost, and high resolution, localized stiffness control, and distributed sensing. I'd love to chat with you at my poster session about our applications and haptic user interfaces in soft robotics. And I also have more fidget toys. Thank you.
Hey everyone, I'm Connor. And so what we did is we took a simple vibrating surface and we used that to transport parts vertically against gravity. We did that using these alternating sticking and slipping phases. So we would stick up with the object and then slip below it, effectively catching it at a lower position. And then we just repeated this over and over again to move that part upward. To test this theory, we built a parallel jaw gripper that can transport a bunch of different parts with different masses, friction coefficients, also different contact types. So we had like plane contact, line contact, point contact as well. And to kind of verify our dynamic model, we also built a test bed. I pointed my phone through a microscope and collected some motion tracking data, and that verified our dynamic model that we were using. If you want to come learn more, play around with the device a little bit. I didn't bring it to turn it on because it's really loud, but if you want to play around with it passively, I'll have that at my poster. Thank you.
Hello everyone, my name is Himadri Basu and I am presenting today trajectory planning problem of a multi-agent system in space applications. The objective of a formation reconfiguration problem is to find a fuel optimal final configuration and thruster commands that allow the agents to move from one formation to the other while avoiding any collisions along the way. The challenges are the target assignment problem is coupled within the trajectory optimization framework, and it gives rise to exponential time complexity because of mixed integer linear programming formulation. And the second issue is the non-convexity of collision avoidance constraints. We present two approaches in our work where we decouple this assignment problem from the optimization algorithm, and these two approaches differ from one another on how collision avoidance constraints are formulated. In the first approach, we find feasible path to fuel optimal final configuration. In the second approach, we find a feasible final configuration with optimal paths towards the terminal locations. In our current work, we are additionally considering the presence of external obstacles and developing a reinforcement learning based maneuvering policy to avoid such obstacles. Thank you. Come check out my poster.
Hi everyone, my name is Wenlong, and today I'll be presenting our recent work, Vox poster. So in this project, we asked the question, how can we enable robots to perform a wide variety of everyday manipulation tasks, like shown on the left, in a zero-shot manner? So what we're looking for is RGBD observation and language instruction in, and 6 staff closed-loop trajectories out. So to do this, we propose to use large language models and vision language models to construct a 3D value maps in the workspace of the robot. And then this is used to guide a motion planner to synthesize the trajectories. If you're interested, please come by our poster to check it out. Thank you.
What if we can farm the open ocean? Our robots are floating farms that grow seaweed and sink the biomass to the bottom of the ocean for gigaton-scale carbon removal. However, these farms are huge and clunky, so pushing them through water needs a lot of energy. Our key insight is that we can operate them with 1,000 times less energy by letting them drift on currents and using small propulsion strategically to switch the currents when necessary. We call that hitchhiking in ocean currents. We developed various methods combining dynamic programming and machine learning to navigate them reliably despite high forecast errors, to maximize growth over months, even though forecasts are only 5 days out, to stay safe, and to operate them as multi-agent flocks. Come by to chat about it.
Hello, everyone. My name is Rohan Jha. It's my great pleasure here to introduce you NOR, neural signal-operated intelligent robots for everyday activities. NOR is a brain-robot interface. It's our new system that allows humans to directly control robots using their brain signals. In particular, we use non-invasive EEG device to record human brain activities, use that to infer human intention, and pass that intention to our robots. We show that on the right here, with NOR, robots can assist humans in challenging long-horizon daily activities, such as cooking, cleaning, playing tic-tac-toe with your friends, and even petting your robot dog. And if you're interested, please come to see us at our poster. Thank you very much.
That was all the student lightning talks for this morning. Now we have our coffee break and poster session. Please try to be back around 11 a.m.